chapter onto polymer physics for this semester, which is going to be on viscoelasticity, okay, and some mechanically stimulated phenomena in terms of viscoelasticity. I hope we will finish the normal classes by this Thursday, and then next week we will have one mock exam to help you familiarize with the concept of the exam and the form of the exam, where initially I will give you some time to solve some answers of the exam just by yourselves, and then we will discuss the exam mock exam answers together. Sorry, and then we will do a couple of revision classes where I will talk about let's say the most important aspects and topics from each chapter. Well, I will give you also some revision slides to have a look, which are going to be the slides that we use throughout the year and throughout the semester. And finally, we will do one Q&A session, probably during the last session, okay? So the last thing we were talking yesterday was this stress decomposition, okay? What essentially, how this main curve of the total stress strain curve, how does this essentially take place, how this originates? And this originates from the contribution of two factors, the intermolecular resistance and the network component, okay? And we said that in mechanical properties, when we do these 1D models, essentially, where essentially it's like that, we use springs like this one and dashpots like this one to represent the properties of an elastic element. Spring is the elastic element, and dashpot is the viscous element. I told you, in order to consider a dashpot, how it operates, essentially, you need to think of a bucket full of honey, and you're putting a piston in there where you're pushing the honey in there, okay? This is viscous. Your hand or the piston does not move freely within the honey, okay? And that is essentially a representation of how a dashpot operates. So the intermolecular contribution to the total curve has to do with the spring, a combination of spring and dashpot. The spring essentially accounts for the elastic response at small strains, that is the modulus, while the dashpot corresponds to a contribution regarding yield, okay? Because we said that yield essentially activates the motion of the chains on a segmental scale. After the yield, the chains are essentially the main part of the chain is essentially under movement. But of course, in this case, it's not temperature related, as we saw in these graphs, okay, where essentially we overcome the TG by supplying more thermal energy. In this case, we supply more strain, okay? So the contribution of the dashpot essentially in this 1D model is towards the yield. And the second part of this 1D model, viscoelastic or viscoplastic model, that's how they usually are called, is this network component, okay, which is represented by just one spring. And this spring essentially guides the ultimate elongation and strain hardening. Okay, so you can realize that the intermolecular contribution to the stress strain curve is all the way up to, why is this that? Okay. Is all the way up to this region, let's say, where we have an activation of chain motion on segmental scale. After the yield point, we have movement of the chains of the main chain, while the network contribution starts from no, not that one. Let me use that one. Starts from that place essentially, where essentially it dictates the strain hardening, okay, and also how much the polymer width elongate. So this takes place through progressive alignment and locking of exchange chains between entanglements or crosslinks. Now let's have a look a bit more at strain hardening. And we already said that above the glass transition temperature, the chain motion at plastic flow is comparable to the situation, okay? So after the yield point, after yield, sigma yield, we have an activation of large-scale segmental motion, okay? Sorry about that. So we have two indications that the strain hardening has an entropic nature, okay? First of all, strain hardening can be reversible, and we will see that in a second. And also, we already have seen the equation regarding the rubber elasticity, okay? And we will examine that a bit more, okay? So let's have a look at the reversibility of deformation. If we have a sample that looks like that, and we have a necking, okay, this is the neck, okay? If we hit the polymer above the DG at this stage, so we stop applying strain, and we obtain this sample which has the neck here. And we said that at the neck, what is the situation of the chains? The situation of the chains is that they're getting oriented progressively, okay? We have surpassed orient themselves along the stressing direction, okay? Chain what we do is give more thermal energy to the chains, and because we give more thermal energy to the chains, we activate segmental mobility even more. However, because we're not pulling, in this case, the chains are coiling back again to their original state, and that lets them return to the original geometry. Okay? So I repeat, we have a sample as it is with the neck, okay? And we hit it at temperatures higher than glass transition, and of course, and obviously lower than Tm, okay? And the chains which are slightly starting to get oriented, they get enough mobility, and because they get enough mobility, they start getting entangled again, okay? Because they start moving again, they're relaxing, and this is essentially a thermally induced segmental mobility, and that helps the sample return to the original geometry. Of course, that takes place mainly at low and medium values of plastic. If you stretch the sample very, very much, okay, if you create a very long neck, it is very difficult to achieve a full recovery of the original geometry. Of course, this is for glassy polymers, so we cannot extend our neck as much, okay, as we can do for semi-crystalline materials, where essentially we can extend the polymers out. But still, this takes place mainly at low and medium values of plastic deformation, okay? And also something interesting in terms of the reversibility and of nature of stress hardening. The most entropic nature materials are elastomers, okay? So we have seen already that the true stress of elastomers has to do with the network density, okay? So the more dense the sample is, the higher network density, the more higher will be the ultimate tensile stress, okay? So if there is a chain scission where the covalent bonds in the main chain fracture, fail, and I repeat, I told you that in one of the previous classes, we talked mainly about the covalent bonds because the covalent bonds are the most strong ones, okay? First, we have a failure of the weaker bonds, such as the van der Waals forces, the London forces, intermolecular forces, and so on. Then we have the hydrogen bonds, and then we ultimately have the covalent bonds. Once the covalent bonds break, then there's nothing to keep the carbon-carbon bonds solid, okay, and prevent them from fracturing or failing, okay. And the second mechanism of failure is chain slippage, where the entanglement network completely falls apart. Okay. It is very difficult to distinguish every time which is the exact mechanism that leads to a failure. Okay. But the most popular and the most easy way for polymers to fail is by chain slippage. Of course, if we increase the temperature, so we perform a tensile test with under increased temperature, we have an activation of the segmental mobility of the chains. And because the chains are able to move more freely because they have this energy from temperature, this entanglement dominates, okay? Because in this case, they display a rubbery behavior. While at very low temperatures, let me use another color, while at very low temperature, chain dominates. In this case, of course, as you would expect, we have a glassy behavior. So at low temperatures, the chains are interlocked with each other. They don't have any thermal energy, so they don't move around, okay? So the entanglement network keeps constant, but the covalent bonds are failing and chain scission dominates. And obviously, the molecular weight, as I told you, and as we discussed a couple of times, the molecular weight is very important towards the behavior of the polymers, the mechanical behavior of the polymers. As you would expect, the ultimate tensile strength is determined by the molecular weight of our polymers. So the longer the length, the longer the chains, the more entanglements that they have, okay? So the more entanglements they have, the higher tensile strength, okay? So the Z average molar mass, which has to do, I repeat for 100th time, has to do with the length of the chains. So the higher the MZ, more entanglements or more entangled chains, and that leads to higher ultimate tensile strength. Okay. We also spoke in the past about the effect of MZ onto the mechanical properties as a function of temperature. You remember that in this modulus versus temperature graph, disentanglement takes place in this rubbery plateau. Okay, so the higher MZ, the longer the plateau, the rubbery plateau. Because in this case, disentanglement takes place with the increase of temperature, okay? And when we have a complete disentanglement and slippage of the chains, then at this stage we have a temperature that is close to the melting point and where the chains can completely slide against each other, okay? As you can see, the molecular weight mainly affects tensile properties, and it only affects the ultimate tensile strength. So there is almost no influence on molecular weight on stress, strain softening, strain hardening, but only ultimate tensile strength is weight dependent. Sorry, did I get a message from the DAs? Okay, no. Now, there is also the case of a brittle failure, which essentially we discussed yesterday. So the stress strain curve for amorphous polymer. Okay, I may have generous. So the material fails very fast because of crazing. Okay, crazing is, as we said, a very highly concentrated phenomenon, highly concentrated stress state. Okay, where essentially it takes place through these three steps. Where firstly we have the formation of a localized plastic zone. This takes place randomly. Okay, we cannot predict where it will take place. And then after this localized plastic zone is formed, there is a triaxial stress strain that builds up around this zone. So this area of the polymer is very highly concentrated with stress, and because this triaxial stress leads to the formation of voids, and these voids essentially start opening up. We have the elongation of the polymer ligament, and then we have failure. And it is important that crazing takes place, of course, if the critical stress is reached before the yield stress. Okay, so the material does not have any plastic deformation, any permanent deformation. Yes, we talked about all these. Okay, how? Of course, now we can try to modify. As I told you, we generally try to mess up and play with the polymers in order to affect the properties with a number of reasons, with a number of methods, and how to prevent strain localization. Strain localization is essentially crazing. How to prevent brittle fracture, essentially. And the way to do that is by lowering the yield point, okay, and or increasing the strain hardening, okay. So by two main methods, by addition of rubber particles, which we saw yesterday, what we do is that we achieve the strain localization. We achieve a wide distribution of strain, and we achieve a delay of the crack propagation within a polymer, so avoid any brittle fracture. Okay, while also we also discussed extensively about the addition of plasticizers, which make our polymer softer and reduce also the modulus. Okay, so we can prevent localization and brittle fracture. However, by the addition of rubber particles and addition of plasticizers, we lose a couple of things. We lose essentially lower the modulus, and we lower the yield point of our material. Okay, and also in order to increase the ultimate tensile strength, we can have enhanced cross-linking and pre-orientation for our materials. Okay, because by using more cross-links, then the polymer finds it more easy to break, and that leads to an increase or increase ultimate tensile strength, increase cross-linking, increase pre-orientation, and maybe I would say increased MZ. Okay, because we said that when we have an increased Z average molecular weight, we have longer chains. Longer chains lead to more entanglements, okay? Okay. And that is generally how some of the methods that we apply in order to affect and control the ultimate properties of ultimate mechanical properties of a polymer. We saw these. Yes, and this is the plastic deformation, essentially how it takes place by chain slippage and crystal slippage. Okay, we talked about that, what happens after the yield stress, and the yield stress is generally determined by crystallinity. So it depends on how many crystalline areas do we generally have and how long these are, and what will happen after the yield, where they break, and if there are also time molecules between them or not. So it is a bit complex phenomenon. Two definitions for the molecular background. The yield can be due to chain slippage or crystal slip. Well, this one, the crystal slippage, being a more common case. And that's pretty much it for the mechanical properties. We will. I will give you on Thursday, when we will finish the viscoelasticity class. We will do a quick revision on. Oh, I didn't import the new. Give me a second. What do I do now? Let me stop sharing for a second. I will give you tomorrow some, not tomorrow, again on Thursday, some multiple choice questions, so we can go through them together. Now we will be talking about viscoelasticity, which is the final chapter in what I did yesterday. Yeah, that's where the confusion came. I removed 3 slides from the slides that I had on QM Plus, which we will not be discussing because one of them were wrong, and one of them were, 2 of them had problems which we'll not be discussing, so not that important. Okay, viscoelasticity, share. Okay. And now for that, I want to view single page. Okay. So let's go into the final chapter of course, viscoelasticity, where viscoelasticity is a very interesting aspect of polymer behavior. Given that polymers, as we said already, are viscoelastic, okay? They exhibit both viscous and elastic behavior. So polymers exhibit behavior, okay? But let's have a look at what is individual behaviors, okay? Viscous materials are liquids, okay? And liquids, as we know, they deform continuously under stress, okay? So viscous materials such as liquids, let's say, And now we have, from viscoelasticity, we can have also elastic materials. Well, elastic materials are a bit idealized because it's not very easy to achieve them in the long range, okay, at large stresses and or strains. So what happens with elastic materials is that they deform under stress, but once stress is removed, they can recover their original shape, okay? So they deform, but stress okay? These are elastic materials. It's very simple. Apply stress, okay, or strain, and once you leave the stress, the material recovers to its original position. That is the definition of elastic materials. Now, polymers. We said that polymers are viscoelastic, which makes them very, very interesting. So let's see how polymers behave. At low temperatures or high strain rates, what did we say the behavior of a polymer is at low temperature? Mechanically, what is the type of behavior for a polymer? Low temperature or very high strain rate. When we apply very fast strain to the polymer, what is the behavior? I got one answer. Indeed, the behavior is glass-like. On the other hand, at higher temperatures or low strain rates, the behavior is, I don't know what I used, but is rubber-like, okay? However, we don't always have high temperatures or very low strain rates or very low temperatures and very high strain rates. What usually takes place is that we have intermediate strain rates or temperatures. And that leads to a viscoelastic behavior, which we will be examining. Okay? A bit messy slide, but don't worry, I'll give you, I'll provide this to you. Okay, so polymers are viscoelastic materials, and we will see the behavior in terms of the viscoelastic character, essentially. So we will be talking about the elastic behavior and the viscous behavior, obviously, and the viscoelastic, which is a combination of the three. Something very interesting and very important is the creep behavior of a polymer. Okay, the creep behavior of a polymer essentially defines how a polymer behaves under a constant stress. Okay. Consider you have a chewing gum. Okay. You're chewing gum. You stretch it like that, and you keep it like that over, I don't know, a whole day. Initially, chewing gum will be straight or have a small curvature, but because of the creep behavior, because we have a constant stress, the material will essentially deform. Now, stress relaxation is another very interesting behavior of polymers, where essentially stress relaxation is the time-dependent decrease in stress that is required to keep a polymer at constant strain. Okay, let me write it down. Okay, so in this case we have constant strain. In the case of creep, we have constant stress. Here we have constant strain. Okay, we won't be talking about proportionality, but we will talking about the Maxwell and the Voigt model, which are two models that are very widely used in order to model the creep behavior and the relaxation behavior of a polymer. How do we fabricate creep isochrones and the information that we obtain from dynamic mechanical analysis? We have already discussed and mentioned dynamic mechanical analysis multiple times in this course. And can anyone tell me what kind of information can we get from dynamic mechanical analysis? Any idea? If we perform a mechanical analysis, dynamic mechanical analysis test on a polymer, what is the information that we can obtain? You can provide information for different kinds of polymers. It can be semi-crystalline, it can be an elastomer, it can be a resin. Anyone? Dynamic mechanical analysis or dynamic mechanical thermal analysis. It's a long name. No one remembers. Okay, that's interesting. To answer something, the TG, of course. No, the melt flow index, the melting point, and the glass transition. Indeed, Kalia is right. Kyla is right. Kayla. So indeed, we can take information. We can obtain information regarding the transition temperatures. That is mainly the glass transition at the melting point. And also we can obtain information such as the modulus versus temperature graph. Okay, all these graphs that we plot almost every day, modulus versus temperature, these originate from DMA, okay? Yes, this is definitions for viscous materials, viscous fluids, or elastic solids that we gave earlier. And viscoelastic materials shows a combination of the two, okay? Both viscous and elastic behavior depending on conditions, and polymers display viscoelastic properties which make their behavior very interesting. Yeah, that is what we said about glass-like or rubber-like behavior depending on temperature, strain rate, okay? Yeah, and creep and relaxation is part of the viscoelastic properties of a polymer, okay? Because of we're generally in an intermediate range of temperatures and strain rates. And obviously, creep, as I told you, is very important for practical engineering applications because polymers are generally used in applications that are under stress for long times. Okay, so because of that, before we apply a polymer onto such an application, we want to know how the polymer will behave. Okay, what is the exact let's say what is the exact amount of time the polymer is able to withstand the subjected stress without failure, okay? And by doing so, we do this by knowing its viscoelastic properties and modeling its viscoelastic properties, mainly with the models that we will see, the Maxwell model and the Voigt model, okay? Yeah, viscoelasticity is a very old topic. Uh, Here it's 1831. So these guys such as Maxwell, Mendibra, and Kelvin. I'm not sure where Kelvin was from. Cambridge? Not sure. Anyway, these guys were studying creep and recovery for glasses, metals, and rubbers, as you would expect. Polymers, synthetic polymers, was significantly after their time. So polymers started being grown at 1930s or so, synthetic polymers. So, but their original work on the viscoelasticity of the other materials has been adopted for the case of polymers. Let's take a 10-minute break now, and we will resume with an introduction to viscoelasticity for polymeric materials. Okay, so see you in 10 minutes. So let's continue with viscoelasticity, and let's have a look at the response of an elastic material versus the response of a viscoelastic material in a loading or unloading cycle. So for elastic materials, when we have a loading and unloading cycle, so essentially what we do, we apply strain, okay, and we remove the strain. We apply strain and we remove the strain. Always this process in an elastic material does not lead to any energy loss, okay, and no permanent deformation. So no energy loss and no permanent deformation, okay. However, for a viscoelastic material, we have this phenomenon that is called hysteresis, okay. As you can see here, we have some energy loss, okay. This is the loading part. This is the unloading part. The phenomenon that is called hysteresis is essentially the phenomenon where the type-dependent dissipation of thermal energy or heat comes from a viscoelastic material, okay? And essentially hysteresis is this area under, is essentially the difference in area under the loading and unloading curve, okay? So this red part here is showing the hysteresis, is showing the dissipation of thermal energy from viscoelastic material. This value is not only a function of the applied load, but also on the rate of the load that is applied, okay? And the origin of hysteresis is essentially heat. Heat comes from the application of strain, okay? And because we apply strain continuously, what we do is we make the chains touch against each other, okay? Slide against each other. And because the chains slide against each other, there is internal friction that is developed, which is translated to heat, okay? So hysteresis, hysteresis is the result of and this friction, of course, is translated to heat. Okay, so this is the energy loss here. During loading and unloading. Okay, so polymers as viscoelastic materials generally display hysteresis cycles, okay? And this heat that is essentially emitted from polymer during loaded and unloaded cycles is essentially lost to the environment. And as a result, the stress strain curve during loading has a higher area under the curve than it does during unloading. and that is where this difference in the two areas is originating. Okay. Now, because polymers are viscoelastic materials, there are a number of phenomena that take place, and we will be discussing extensively. The two more important phenomena that we will be discussing today is creep, today and Thursday, and relaxation. Okay. Creep is a phenomenon where we keep the stress constant and we observe how the strain increases, while in the case of relaxation, we keep the strain constant and we evaluate how the stress decreases. So, stress constant, strain increase, strain constant, stress decrease. Okay? And that is most important. Of course, there are a number of other phenomena that are related to viscoelasticity of polymers, such as what we said already about hysteresis, which is a dissipation of energy. There is the rebound and also the frictional resistance when we roll or when we push a polymer against a certain surfaces. Okay. So let's have a look at creep. Okay. Creep is, as we said, the time-dependent deformation strain under constant stress. Okay, so we have a constant stress, and we measure the strain. Let's have a look at what happens. So we have a polymer, and we apply a constant stress to the specimen at T0. Okay, T0. We apply a stress very fast. We keep the stress constant, and then we remove the stress at T1. Okay. And we want to examine, we want to study what is the response of the polymer under the constant stress. Okay? Because we apply some stress, there is a response in terms of the strain that is applied to the polymer. Okay? So in the beginning, we have an increased strain, a very fast increase of strain, which is called instantaneous elastic strain, or instantaneous elastic deformation. Of course, here in this graph, it's slightly it's slightly more highlighted. Generally, the instantaneous elastic deformation is much smaller, so it looks like that all the time. So it's not very obvious to see. It's smaller generally than what it seems here, but here it's more obvious in order to see. So let me usually the O is very small. Okay, so initially we have, after the instantaneous elastic deformation, we have an increase of the strain for a constant stress. Okay, and then we have the recovery part after T1. Okay, so this is the creep part, and this is the recovery part, or relaxation, let's say. Okay, so generally when we apply stress, the strain increases rapidly. And then after we remove the stress, the polymer, the material returns to its original position or has some permanent deformation. Okay. The creep modulus is given by this very simple equation, as you would expect, where the stress is constant and the strain is a function of the time. Okay? An introduction, that is what creep is essentially. We have a constant stress. Come on. And we examine the behavior in terms of strain. Okay? Now, relaxation is slightly different. In this case, we have a constant strain. So relaxation has to do with constant. Okay? So in this case, we have a constant strain and we evaluate the behavior of the polymer in terms of the stress. Okay? Or in other words, the strain relaxation is a time-dependent decrease in stress because the stress always decreases if we want to keep a polymer at a constant strain. Okay? So the time-dependent decrease in stress required to maintain the material at constant strain. So what we do in this case, we apply the strain very fast, okay, at top zero, and we keep the strain constant. What happens here is we have the initial increase of the stress, and then in order to maintain the constant strain, we have an exponential decay of, let's say, I'm not sure if it's fully exponential, but let's say decay of stress sigma. Okay, so when a viscoelastic material is held at constant strain, the stress required to maintain that deformation will decay with time. And that is the stress relaxation modulus G, where sigma stuff is the time-dependent stress, and E is the strain. Okay. So let's have a look at elastic and viscoelastic behavior, given that we will need to model the behavior of a polymer. As we said, polymers have a viscoelastic behavior. So we will first examine the elastic behavior in terms of the excitation and the response. So, and also we will examine the viscous behavior in order of excitation and response, and we will see how the combination of two leads to the viscoelastic behavior. So the elastic behavior is modeled by a spring. Okay. As we saw already for in the previous class and today as well, when we model the mechanical properties of polymers, we said we approximate the mechanical properties with combinations of springs and dashpots. Okay. So for elastic behavior, the polymer is deformed, but because of its elastic behavior, the polymer reverts instantaneously to the original shape when the load is removed. Okay, and that is essentially represented by Hooke's law, where if we differentiate Hooke's law as well as a function of time as well. Okay, so this is the excitation, and the response is identical in terms of stress. Okay, and this is the loading and unloading curve or cycle. Okay, this is the elastic behavior. The viscous behavior, as we said, is a bit more complex and is represented by a dashpot. This is a dashpot, and essentially this behavior is completely viscous behavior. Okay, essentially is, as I told you, gives an information regarding how we push, let's say, a piston within a viscous liquid, such as honey or oil. So in this case, the part has a shape, and it flows eventually under the action of external forces. So if we have the excitation of at T0, T1, and T2, okay? So T0 starts here, T1 is here, and T2 is here, okay? So this is the response in terms of stress over time. And the viscous behavior is described by Newton's law for sigma equals eta dE over dt. This one is the derivative over time, okay? We've said that in the past. Okay? And finally, we can see that for viscoelastic behavior, when we have an excitation like that, T0, T1, T2, T0, T1, and T2, you can see that the behavior is much more complex. This is just an example of a viscoelastic behavior. Okay, you can the response can be different. It does not certainly need to have the same shape, and obviously in terms of the energy in a loading unloading cycle, it does not have to go away to negative stresses, but it can go like that, as we saw already. And this area here is the energy lost. This is a hysteresis cycle. Okay. Yeah. So in terms of a kind of a summary, in terms of the creep behavior, we have excitation, constant stress, and an increase of strain. Okay, with constant stress, increasing. While in the case of the relaxation, we have, as I said, constant strain and decreasing stress. Okay. Now, let's go to something a bit more interesting and a bit slightly not too much complex. And let's examine the two main mechanical models that are used for the description of creep and relaxation. Okay. So as we said, the basic components that we use in order to model the mechanical behavior of a polymer is an elastic spring and a viscous dashpot. Okay, the spring obeys Hooke's law, and the viscous dashpot obeys Newton's law. Okay, so based on different combinations of we can essentially approximate viscoelastic behavior of a polymer. So here we have the Maxwell model. Well, as we will see in a second, in the Maxwell model, the spring and the dashpot are connected in the Voigt model, where spring and the dashpot are connected in parallel. This is the standard linear solid model, where this is similar to the model that we saw earlier from for the stress strain curve of for neck. okay, and it's combined. It is a combination of spring connected in parallel with a dashboard and another spring which are in series. Okay. Yes. So that is what we already discussed. These equations, we will be using them in a second in order to reach the final equations for Maxwell model and the void model. Okay. So Hooke's law is the law that we use generally for the elastic model, and Newton's law is for the dashpot. Okay. Now let's evaluate. No. Let me give you a brief introduction. Let's evaluate the Maxwell model, and let's see how the final equations for the Maxwell model are derived. And these were derived essentially in the 19th century by Maxwell. Okay, so we're talking about very obvious, essentially were used in order to observe the time-dependent mechanical behavior of viscous materials such as tar or pitch. Okay, so let's go to the notes. Let's make a new note. Today is the 23rd. 23rd, right? Yeah, 23rd of November. And let's have a look at the Maxwell model. I should point out that both the Maxwell model and the void model are highly idealized models. So they are not always correct, and we will see in which aspects each model is correct and is able to model more accurately the creep or the relaxation behavior. Okay. So for the Maxwell model, we have a spring and dashpot in series. Okay. So in this case, the dashpot represents the viscous element, while the spring represents the elastic element. And the strain E2 and E1, okay? Strain usually is represented by E or E, okay? In this case, we will use the English E because there are some slides in the notes that have E English E, okay? So in this case, under the action of stress, the overall strain is E equals E1 plus E2, okay? And let's say this is equation 1. Now, we can see the two elements are in series, okay? So the stress in this case is identical. So sigma equals to sigma 1 equals to sigma 2. Okay, so let's have a look at the Newton's and Hooke's law for the Hooke's law first for the elastic spring. Okay, so for spring, we have that ds over dt equals to e de1 over dt. Okay, and for the dashpot, we have the Newton's model, okay, and the Newton's law, which is S equals to dE2 over d tau over times the viscosity. Okay. Now, if we differentiate equation 1, what do we get? dE over dt, dE1 over dt, plus dE2 over dt. And that gives us dE over dt. dE1 over dt from here, okay? And dE2 over dt we solve from Coulomb's law, from Newton's law, sorry. So we substitute Coulomb's law and Newton's law onto the differentiated equation 1, and we obtain dE over dt is 1 over E S over dt plus sigma over eta. Okay, and let's say this is equation number 2. Okay, now let's apply this equation onto the situation of creep and relaxation. So for creep, we have a constant stress. Okay. Sigma is sigma 0, and also the derivative of the sigma tau equals 0. Okay. So for creep, the Maxwell model essentially expects a dependency of dE over dt equal to sigma 0 over eta. Okay, that is the equation that, according to Maxwell, creep is expected to be represented by this equation. Now, for stress relaxation, in this case, we have strain is constant. Okay. E equals to E0 and dE over d tau equals to 0. And then equation 2 becomes 0 equals to 1 over E ds over dt plus sigma over eta. So ds over s equals to minus E over eta dt. So after integration, so now we need to integrate this equation, okay? So after integration, and for t equals to 0, and t to sigma 0, we obtain sigma equals sigma 0 exponent eta, and then the final equation is sigma equals sigma 0 exponent of minus tau to tau 0. Because we already said that we have already given the definition of T0 equals to the relaxation time where T0 equals to eta over epsilon, and sigma 0 is the initial stress. Okay, so the creep equation from Maxwell's theory. Maxwell's theory is this one, and for creep one is this one. Now let's go ahead and try to plot this for the two let's say mechanical behaviors for creep and relaxation. So for creep, we say we have constant stress and we study the strain over time. So we have strain over time. The equation is this one, okay? D over the top. Let me write it down. Sigma 0, okay? So from this equation, the graph that is obtained looks like that, okay? Where sigma 0 over eta is the slope of this curve, of this red curve, and this original part here is given by sigma 0 over E, okay? As you can see, this graph does not represent very well the behavior of strain under constant stress, okay? Would expect to see something like that would look like that, okay? But this graph does not look like that, so as a result, we can say that Maxwell's model cannot be used to study creep behavior. Okay, that is for creep. Now let's have a look at the relaxation curve. The relaxation, we said that we have a constant strain and we measure the stress over time, okay? Time is here, stress here, okay? So in this case, we have this equation, sigma 0 exponent of minus time over the relaxation time, okay? So this behavior is represented by a graph that looks like that, okay? Here, this equals to E times E0, okay? And as you can see, we have an exponential decay of stress. And that is what we would expect, okay? We already saw that in the previous slides that when we apply a constant strain, the stress is exponentially decreasing. So relaxation this is creep, okay? So Maxwell's model can be used to study the relaxation behavior of polymers. Here the keyword is cannot, here is can, okay? So this is Maxwell model. It can be can approximate very well the relaxation behavior of polymers. This equation is exponential decay of stress. Well, it cannot predict very accurately the the creep behavior of polymers. Okay. Now, the second model that we have is the void model. Sometimes it's called Kelvin. Okay. So in this void model or Kelvin model, as we said, the spring and the dashpot are connected in parallel. Okay. So here we have a spring and a dashpot. Okay. So the spring represents elastic parameter sigma 1, and is the dashpot is the viscous phenomena and sigma 2. Here we have a connection in parallel, and we know that the strains in this case are uniform because we have a parallel connection. Okay, because we have a parallel connection, the strain is the same anywhere in the model, and the stress is sigma equals to sigma 1 plus sigma 2, and that is our equation 1. And we already know from the spring that sigma 1 equals to E over E, okay? And for the dashpot, we know that sigma 2 equals to eta dE over dt from Newton's law. This is Hooke's law. This is Newton's law. Okay, so again, similar to what we did previously for the Maxwell model, we go to equation 1 and we essentially substitute sigma 1 and sigma 2. Sigma equals to E plus eta dE over dt. And we solve for dE over dt equals to sigma eta minus E times E over eta. But when the stress is held constant, sigma is equal to sigma 0. So in this case, dE over dt plus E over eta equals sigma 0 over eta. And after integration, okay, E equals to sigma 0 over epsilon 1 minus exponent minus E t over eta. How much time do we have? Okay, 5 more minutes. I think that should be okay. So the strain is given by this equation, sigma 0 over E 1 minus exponent minus t over tau 0, where tau 0, we already said before that it is the relaxation time. Okay, where it is? It is. So from Voigt's equation, we get this dependency of strain when the polymer undergoes creep. So the strain rate decreases with time. So polymer undergoing creep, strain since E given by sigma 0 over E as T is approximated to infinity. Okay, so this equation in terms of the creep behavior, to give you the graph immediately in this case, for creep, we say we have constant stress and we study the strain, so the behavior is given like that over time. Okay, from equation, let's say 2. And indeed, the void model, so, and this part here, okay, so the void model okay. We said before that the creep model is not able to study the creep behavior. The Maxwell model is not able to study the creep behavior of polymers. The void model is able to study the creep behavior of polymers. Okay, and let's have a look at what's happening with stress relaxation. So for stress relaxation, we have E equals to E0. So the derivative of dE over tau equals to 0. And the previous equation becomes that so the void model tells us that stress relaxation can be approximated with an equation that looks like that. If we plot that, we can see stress relaxation. We said we keep the strain constant and we measure the stress over time, okay? So if we plot that, it looks like that, where this part here is equal to E times E0, okay? And as you can see, the void model cannot be used to study okay. So in order to study the creep and the relaxation behavior of polymers with two of the simplest models that we can fabricate, the Maxwell and the void model,